Hello friends, how are you all today? Have you ever wondered what are Jacobians and how we can use Jacobians to solve the engineering problems? It's coming up right now. So now we know that we have the values of dou f by dou u and dou f by dou v. So I apply the chain rule to dou f by dou u and dou f by dou v in slightly different fashion. Okay, so let me write the dou f by dou u first. Using the chain rule, we can write it in this way, right? That is dou f by dou x into dou x by dou u. It's valid. Plus dou f by dou y into dou y by dou u. This is the chain rule, right? The same chain rule I can apply. So I will call this by equation number. Let me call it. Okay, this is 9. Similarly, I can write dou f by dou v is equal to, that is dou f by dou x into dou x by dou v plus dou f by dou y into dou y by dou v. This is number 10. Now I can see that the order needs to be slightly modified before we proceed further to get any standard format of results. So what I do, I'll just switching the order. Okay, so switching the orders of the products, right? Products in equation number 9 and equation number 10, they're going to give me the following. Okay, I write once again, that is dou f by dou u is equal to, first I write the dou x by dou u, then I write the dou f by dou x plus the dou y by dou u into dou f by dou y by dou u, dou f by dou y. Okay, I'll call this as equation number 10. Similarly, I write the dou f by dou v part. This can be written like dou x by dou v into dou f by dou x plus dou y by dou v into dou f by dou y. Let me call this as equation number 2. In equation 11 and 12, we can see that the f which is present is a function. It was f of x comma y, and we wanted to convert that into u comma v, f of u comma v. So that f, what we are seeing there, is a function. So it's a general function. So I can try to eliminate. I can try to write the same functions in 11 and 12 once again without the term f, which means these equations are actually being converted into the operator format. Okay, so I'll write f is an arbitrary function, right? So we actually can neglect it whenever we want to write the equation number 11 and 12 as operators. Okay, therefore I can write the operator equations are, right, from 11 and 12 I'm writing, that is, it's just the dou by dou u, eliminate the f from that. So when you want to calculate the dou by dou u, you can simply write the dou x by dou u into dou f by dou x. So f is not there, it's just dou by dou x, plus the second half would be dou y by dou u into dou by dou y. That will be equation number 13 for us. Similarly, the second, that's equation number 12, can be modified as dou by dou v is equal to dou x by dou v into dou by dou x plus dou y by dou v into dou by dou y. Equation number 14. Now, let us say that we want to write a computer program for this, right? Then our objective will be obviously to represent these equations in the form of a matrix. All right, so I'll write that as well. So therefore, the equation format, therefore, I can write the matrix notation. Matrix notation of 13 and 14 can be simply write them inside the matrix notation. This is dou u, sorry, my mistake, it's just dou by dou u, first term, and second term will be dou by dou v. This is inside the, so that it becomes a matrix. So this has to be, I can see that this dou by dou x, dou by dou y is common for both the equations, so they will be inside a matrix. The other four terms, specifically dou x by dou u, dou y by dou u, dou x by dou v, dou y by dou u, will be inside the environment, so that the matrix multiplication will take place to get the answer that is present on the left hand side. Okay, so let's write that equation now. This is dou x by dou u, first one, then dou y by dou u, dou x by dou v, and this is dou y by dou v. This is one equation, one matrix, and the second matrix should be, this is dou by dou x and the dou by dou y. I'm going to call this as equation number 15. The square bracket or the square matrix present in the right hand side of equation number 15 is what we call as the Jacobian matrix. To represent that, we use the notation that is capital J. See, we are writing in terms of x, y, we are converting it into u and v. So the standard notation used for this kind of Jacobian matrix is Jx comma y over u comma v. Okay, this is nothing but the dou x by dou u, dou y by dou v, dou x by v, dou y by dou v. That means the same equation, number 15, can be rewritten as the dou by dou u, dou by dou v is equal to, this is j x comma y over v comma v into this matrix, right? The dou by dou x, dou by dou y. All right, so this is what we call as equation number 16. From the basics of linear algebra, whenever we want to calculate the matrix, which is already being represented as a product of two other matrices, right, we can use the inverse logic to calculate the value of the matrix. For example, in this case, if at all I want to calculate this matrix, okay, I need to take the J matrix to the other side, right? So which makes it like what we can write now. All right, so let's write that now. This implies, right, we are going to hold on to the one equation which we are going to write now for some time, and then we'll prove an important property of the Jacobian. So this implies if you want to calculate the dou by dou x and dou by dou y matrix, right, I can take this to the left hand side. The j will go to the left hand side as j inverse, because it's a matrix, right? J inverse x comma y over u comma v into, right, the dou by dou u, dou by dou v. So call this as equation number 7. Let's hold on to this for some time, and then we'll prove that what is this matrix. How do you calculate the J inverse? Anyway, using the matrix algebra, we can calculate the J inverse, right? But there has to be another method, because using x, y, u, v, I should be able to represent, right? So that's my objective for the time being. So for that purpose, what I do, I'll bring the matrix once again. So that is the matrix, the equation number 1 and 2. I'll start from equation number 1 and 2 once again. Let me copy that. Now, what we do here is, right, I copied this down. Now, fine. So, like we did earlier, I'll try to do this quickly because we already know the steps, right? I directly try to move this to the left side. That is dou f by dou x is equal to, there is a dou x, okay, dou u by dou x into dou f by dou u plus this is dou v by dou x into dou f by dou v. So I'll call this as equation number, I think the previous equation was 17, so I'll call this as 18. Very similar to this, let's dou f by the dou v of the dou y should be equal to, this is dou u by dou y into dou f by dou u plus this is dou v by dou y into dou f by dou v, equation number 19. Alright, now you can eliminate the f and write the operator equation. Okay. The operator equations are as That means you can simply eliminate f. So the dou by dou x will be equal to dou u by dou x into dou by dou u plus dou v by dou x into dou by dou v. Similarly, the dou by dou y is equal to, this is dou u by dou y into dou by dou u plus dou v by dou y into the dou by dou v. So this is equation number 20 followed by equation number 21. Right? So convert the equation number 20 and 21 to the matrix format. Alright, so now we'll write the matrix format. Alright, so the matrix format will be the dou by dou x, the dou by dou y is equal to, this is dou u by dou x, dou u by dou y, dou v by dou x, this is dou v by dou y times, I'm supposed to multiply the dou by dou u first, then dou by dou v. So call this equation number 22, where I'm going to call the j. I'll change the format. This format I'm going to write. I'm trying to write u comma v now. So this is u comma v divided by or over x comma y. Right? So you can see that u, v are over x and y in the square matrix. So that's why this is the notation. This is given by the dou u by dou x. This is dou v by dou x, dou u by dou y, dou v by dou y. Okay, this is 23. Therefore, I can rewrite the equation number 22 as follows. So equation number 22 becomes the dou by dou x, dou by dou y is equal to Jacobian matrix. Now this is in terms of u comma v over x comma y, into multiply this matrix with the dou by dou u, dou by dou v. Let's call this as equation number 24. Now let us see what we had written in equation number 7 so that we can compare it with this equation number 24. All right, so in equation number 17 we had written this part with the LHS dou by dou x and dou by dou y. We have the same thing, dou by dou u, dou by dou v, dou by dou u, dou by, which means these two equations must be same. These two matrices must be same. Then only it's possible, right? So the from equation number 17 and 24, we come to know that, right, one very important property of Jacobian, that is, I'll write now. So equation number 24 should be equal to equation number 17 right? This implies I can write this: the J inverse of x comma y over u comma v should be the Jacobian matrix of u comma v over x comma y, right? And also I'll call this is equation number 24 over then 25, and this implies from the basics of matrix algebra I can write any matrix into its inverse is an identity matrix, correct? So let's write that. Therefore, right, if I write j x comma y over u comma v multiplied by j, this is u comma v over x comma y, as they are the inverses of each other, I'm going to get I. Okay, one very important property of the Jacobian matrix. I'll call this equation number 26. So far, we have seen what Jacobians are, how to represent them, what are their basic properties. Now, we'll try to apply the Jacobians in three standard transformations related to the coordinate systems. The first one, so first we are going to see the conversion from the Cartesian coordinate system to the plane polar coordinates. This is our first objective. All right. Now, let's consider a diagram. So this is the diagram. Now, we can see here that the original, there is a point, let's say the point is, there is a curve and we have a point over here, and that point can be represented either in the form of x and y. So x and y are the axes which have been marked, and its coordinates are x comma y. At the same time, if you want to change it from x comma y to r comma theta, all right, then this is the transformation. I'll write the transformation over here as t. This is the transformation. All right, then I can use the Jacobian to find the Jacobian matrix to do that. All right, let's see how we can do it. So considering this diagram, I know some standard transformation. It's already well known, so we can directly write it as follows. So the transformation that we are going to use we can write, say x is equal to r cos phi, and y will be equal to r sin phi. We use these two equations as the transformation rule. That's the relationship between r phi with x and y. We know that they're pretty standard, right? Once you know this, I can directly write I can directly write, say, what is dou x by dou r? So this implies the dou x by dou r is equal to, it's just cos phi, correct? I can also write the dou x by dou phi. What is dou x by dou phi? It is minus r sin phi, right? They're pretty basic differentiations. Similarly, I can write the dou y by dou r. So I know that the dou y by dou r is sine of angle phi, and I can also write the dou y by dou phi, which is equal to r cos phi. Okay, let's give some equations now. So I'll call this as equation number 1, this equation number 2. Right. From the given diagram, it's very clear, and I can use the transformations as a standard transformation between r and phi with respect to x and y. Right. Now, if you want to write, we use a very similar logic what we used earlier whenever we were dealing with the Jacobian matrices in the previous section. So directly apply the chain rule and find out what is the dou by dou r and dou by dou phi. That's my objective. So the I can write the operator equations in a pretty straightforward way. That is the dou by dou r is equal to, right? We can look back to the previous set of equations what we had derived. Same thing I'm writing here, but without the f. Okay, there is no u. Instead of u, I'm writing r. Instead of v, I'm writing phi here. Okay, so this is dou x by dou r into, it is dou by dou x plus, I can write the dou y by dou r into, this is dou by dou y. So if you recall, we had, this was u in the previous section, this was u, this was u. So dou by dou u equal to something we had written in the operator equations of the previous section. Same thing I'm applying here, right? Now I can actually substitute this because I know what is dou x by dou r, dou y by dou r. Right, from equation 2 I can substitute and write this equal to, so see, dou x by dou r is cos phi, dou y by dou r is sin phi. Let's simply substitute. So that is equal to this, I can write the cos of phi into dou by dou x plus sin phi into dou by dou y. All right. Similarly, let's write the operator equation for dou by dou phi. This is equal to, let's recall what we did in the previous section and write this. So there we had the dou x by dou phi into, this is dou by dou x plus the dou y by dou phi into dou by dou y. So once again, I have those values available here. Dou x by dou phi, which is required here. Dou y by dou phi, that's also required. I can substitute and get back the proper equation. All right. So this is equal to minus r sin phi into dou by dou x plus, I think we have r cos phi dou by dou y. Okay, this is equation, I'm going to call this as equation number 3. All right. Similarly, I can actually write a equation which is required to calculate the other operator equations, right? You can actually solve these above simultaneous equations to get the values of dou x by dou r, right? Dou x by dou r, dou x by dou phi, dou y by dou r, dou y by dou phi. Using them, we can actually calculate what is dou by dou x, right? Because I have dou by dou r, dou by dou phi available readily here, right? I can actually solve these same simultaneous equations to get the values of dou by dou x and the dou by dou y. Now we need to solve the simultaneous equations represented by the operator equations of equation number 3 to get the values of dou by dou x and dou by dou y. Okay. Equations. So let's observe something. So this part and this part, I want to make them equal so that I can cancel the dou by dou y part in both of them. So in the first part of my equation 3, I need to multiply by r cos phi, and the second equation of this equation I need to multiply by simply sin phi. All right, let's do that and write the equation. So I have sin phi already there, r cos phi, I'm going to multiply. So that is r cos phi into dou by dou r to be equal to r cos square phi dou by dou x plus r cos phi into sin phi, r cos phi into sin phi dou by dou y. This is the first equation. And the second equation I need to multiply by sin phi. So this is sin phi into dou by dou phi to be equal to, I'm multiplying by sin phi. So this is minus r sin square phi into dou by dou x plus r cos phi into sin phi into dou by dou y. Now, what I'm supposed to do, I just have to subtract from one other. Right? Whenever you subtract, these two will get cancelled. That means I'm going to get r cos phi dou by dou r minus sin phi dou by dou phi should be equal to, that is r cos square phi. I can see that r and r are common. I can take a r out. Cos square phi is 1. Second term is negative. Minus of minus becomes plus. Cos square phi plus sin square phi into dou by dou x. Correct? So from this I can write what is dou by dou x. Therefore, dou by dou x is equal to, it's r cancelling on both the sides, right? It's cos phi dou by dou r minus, there is r which is going to the other side, so I have sin phi divided by r into dou by dou phi. So this is the dou by dou x part. I'm going to call this my equation number 4. Okay, and I'm supposed to do the same operation to solve the simultaneous equation represented by equation number 3 once again. So we'll copy the equation number 3 once again over here. Right. Now what I have to do is that I need to cancel this part, right? I don't want this and this. I just want to cancel them out so that I can find the dou by dou y part. Right. Just to do that, let's multiply the equation, first part of the equation number 1 by minus r sine phi. So that gives minus r sine phi into dou by dou r should be equal to minus r sine phi into, there is already a cos phi into dou by dou x, right? I am multiplying by minus r sine phi, so it's minus r sine square phi the dou by dou y. So I need to multiply by cos phi for the second equation. So this is cos phi into dou by dou phi is equal to, this becomes minus r sine phi into cos phi dou by dou x plus r into cos square phi dou by dou. Okay. Now our objective is to get the values for dou by dou y. So we just have to subtract one another. So when you subtract, these two will get cancelled. So I'm left with minus r sine phi dou by dou r minus cos phi dou by dou phi, that's on the left hand side, should be equal to, I have a minus r common, I'll take it out, minus r, second one also becomes negative, I take the minus r out, I have the sine square phi plus cos square phi into dou by dou y. Okay, very much similar to the previous case. This sine square theta plus cos square theta, or sine square phi plus cos square phi is 1 using the trigonometric identity. Right? Now, using that, I can write the dou by dou y, okay, as follows. Therefore, the dou by dou y is equal to, both sides we have negative terms, they are cancelling out. So I have, I'm left with the sine phi into dou by dou r, plus this is cos phi by r into dou by dou phi. Okay. That's the value of dou by dou y. Let's call this by equation number 5. Now we can compare the same equation, the dou by dou y, with the one equation where we apply the chain rule earlier. Right? Let me write the chain rule now so that I can compare the terms. We had the dou r by dou y into dou by dou r plus this is dou phi by, oh, just a second, it's dou phi by dou y into dou by so far. So by just comparing the two equations, I can write dou r by dou y is this, dou phi by dou y is this. Right? These are the values I want so that I can write my Jacobian. Right? So I'll write the values I'm getting now. So this implies the dou r by dou y is equal to sin phi. The dou phi by dou y is equal to cos phi by r. Okay, two values I got. Two more values I'm going to get from the other equation. That is equation number 4. Let's copy that. Right. This was equation number 4. So here also I can actually make a similar comparison with something like the dou by dou x equal to, I'm supposed to perform dou r by dou x into dou by dou r plus this is dou phi by dou x into dou by dou phi. So simply comparing, I'm going to get this. The values are, this implies dou r by dou x is equal to cos phi. Okay, and the dou phi by dou x is nothing but minus sin phi by r. Let me highlight them so that this is what I'm going to use in the next step to calculate the Jacobian. Okay, now let's write the Jacobian of this. This particular Jacobian, what we are going to write now, I'm going to call this as, so r and phi are on the top, x and y are at the bottom, right? So that's how we write the partial derivatives. So let's write that. Therefore, the Jacobian of r phi over x comma y is equal to, if you remember the equation, we are going to write a determinant now. This is dou r by dou x, dou r by dou y. This is dou phi by dou x, dou phi by dou y. Okay, so just remember, we made a change, like this was u, r was u in earlier case, this was v. Only that's the change we have done so far. Right. So we just have those values present in these two equations. Let us just substitute them first. This is equal to, so dou r by dou x cos phi, dou r by dou y sin phi. Next, dou phi by dou x is minus sin phi by r. Then I need dou phi by dou y, which is cos phi by r. So let's take the determinant of this. It is cos phi into cos phi. So I have cos square of phi divided by r. Minus of minus is plus. This is sin square phi by r. So if I take 1 by r out, cos square phi plus sin square phi is 1. So the answer is 1 by in order to find the other Jacobian, we can use equation number 2, that's as follows. Alright, from this we already have the values of different partial derivatives. We use them to write what is called as j x comma y over r comma phi. The standard way to represent that determinant is first dou x by dou r, dou x by dou phi, dou y by dou r, and dou y by dou phi. So that is nothing but cos phi minus sin phi, which is sin phi cos phi. Simplifying, we get r cos squared phi plus r sin squared phi, which is r into 1, that is equal to r. Alright, so already we have seen that those matrices what we write should be inverse of each other, so that whenever you multiply the determinants you get 1, right? So we can verify that this implies the j r phi over xy, right? Multiply that with j x comma y over r phi. So first value we got 1 by r, this value we are getting r, that's equal.